So good evening everyone, welcome back to our series on tropical machine learning. Today we will be starting with basics of tropical geometry, learning what tropical geometry is, understanding how to actually use it, and so focusing by just on these basics for now, and then we'll focus on how to actually apply it to any basic or arbitrary given machine learning model. Alright, so with that let's start. So first we need to talk about what tropical geometry is, right? So tropical geometry is a certain kind of algebra, namely it is a certain kind of semi-ring. Now you're probably wondering, because most of the people who are coming to this lecture are not exactly coming from a pure math perspective, so they don't know what a semi-ring is. So a semi-ring basically takes a set of numbers, like let's say the real numbers, and it gives you two operations, say some sort of the ring addition or the ring multiplication. Okay, so these two operators are going to take any two entries that belong to your real numbers, and then I'm going to tell them how to add them and how to multiply them. Okay, so over here I've given them as ring addition and ring multiplication, so that is a more general explanation. In typical cases, or for our normal case, we would take the real numbers and we would have normal plus and normal add, normal multiplication. So this is an algebraic structure called a semi-ring. Okay, so most of the times the rings that we're interested in is this ring, so real numbers over addition and scalar multiplication, and the next one is probably integers over addition and scalar multiplication. Okay, so these are our general types of rings. So this is what counts as normal. Now we're going to find out what it means for something tropical. Okay, so for a tropical semi-ring, like I said, we're going to have a set over here. Okay, before we had real numbers as an example, we have a set and we have an addition and a multiplication. So for our tropical semi-ring, the set is going to be the real numbers with either it is going to include infinity, plus infinity, or it is going to include minus infinity. And I'll explain why these two are two different choices. We're then going to define something called tropical addition. Tropical addition. And this is going to be tropical multiplication. Okay, so what are these two operations, right? So tropical geometry was originally called tropical geometry or tropical algebra, let's say. Algebra was originally called max plus algebra or min plus algebra. So these two algebraic structures over here, for example, semi-ring is a kind of algebraic structure, right? Similarly, these two are examples of algebraic structures. So these two algebraic structures come from something called combinatorics, or more specifically, a numerative combinatorics. So it comes from this field. Now, this field gave us min plus and max plus algebras. What are these structures? So over here, look at the name. There's a minimum and there's a plus, right? So this is what are these, this name itself is giving us what our operations are. Okay, so for min plus algebra, we're going to have real numbers union, let's keep this empty for now because I'll just help it make sense. And now for our tropical addition, we're going to have the min function. So this is going to be min a comma b. let's just say it's like any to a comma b belonging to our set, our union, whatever is inside the set, right? And our addition is going, and our tropical multiplication is going to be switched out with addition. So a plus b. Okay. So in a better notation, we say कि instead of saying min a comma b, we say a b, like this. Okay. Now similarly, we derived this as min plus algebra. We've left this bracket still empty, right? So in this bracket, we're going to include an identity element. So an identity element is basically key. If I have an element, if I had an element a, and I had an operation plus over here, and I added it with the identity element, the idea is that it gives me the same element back. So for example, if we had regular plus, what number gives back a again? That's 0. If a was this minimum function, so what number over here would give me back a? So this has to be a number that's always lesser than a, right? What is a number that's lesser than a? That is minus infinity. So that's why over here I said the choice key, we can have minus infinity or plus infinity over here. Okay, so this minus infinity is now it's going to be included in our set. Okay, so that's how you define min plus algebra. Now I'm going to erase the sheet and I'm going to explain how to do max plus algebra. Yeah, so now let's talk about max plus algebra. So in max plus algebra, the idea is the same thing. Let me turn on the drawing. Yeah. All right. So the idea is the same thing. Instead, now we're going to have max and we're going to have plus as our new operations. So tropical plus is going to basically be maximum, and like the max of two scalars from the field. And tropical multiplication is going to be given by regular addition. So now let's just go back to some nicer notation. We, instead of saying max of a plus b, a comma b, we like to say a b, like this. Okay, so this denotes maximum and this denotes minimum. Now we have to define our max plus algebra. So we have our two operations. Now we need to construct the same thing where we have our real numbers union some empty thing, which over here, as we've seen before, will be some sort of identity element, comma, our tropical addition, which now we know is not tropical addition, but rather, let me erase that. Yeah. But it is rather the maximum function, or you could say, I'm just going to write max over here in the bracket, and we have addition as our multiplication. So this is now our new structure. And now we need to define what goes in this bracket over here. So now let's see. Let's write down our identity ka equation again. So we want something a plus b, not b. We want a plus id is equal to a, right? So in this case, we want maximum of two numbers a comma something gives us back a. So what number is always lesser than a? So in this case, the number, okay, I see I've made a mistake here. So in the previous example, I said min of a comma something is always equal to a. So a has to always be lesser than this entry, and this is satisfied by plus infinity. Okay, now that's a mistake that I made. And in this case, max of a comma something is equal to a. That means a has to always be greater than the second entry. So that is satisfied by minus infinity. So now we know that our rings are given by this structure. So for max, we have R union minus infinity, comma, maximum comma addition. This is our max plus algebra. And similarly, we can have R U plus infinity, comma, this minimum plus again. And this is our min plus algebra. Okay, so far this is all the explanation required for understanding what tropical semi-rings are. Okay, now we'll move on to just some shorthand. Okay, so for us to understand now how to apply this, we're going to be learning what it means to tropicalize something. Okay, so tropicalization means what? Tropicalization means the act of taking some sort of expression, like say ax plus b, and tropicalizing it into its tropical counterpart. Tropical counterpart. So that would mean ki this is the act of tropicalization. So the tropical counterpart of this is we're going to replace, this is basically a into x plus b, right? So we're going to replace each of these functions as we knew before. So this is going to be replaced by tropical multiplication, ax, or you could say this dot ax, and this is going to be replaced by tropical addition of b. So now we know that this basically translates to a plus x, okay, and uska maximum with b, okay, or you could say max of a plus x comma b. Okay, so this is the act of tropicalization. So to understand how to go from here to here, we're going to just sort of, for our convenience's sake, try to understand this table. Okay, so a plus b goes to a tropical plus b, which is the same as a max b, or you could say a minimum b, depending on if you're working on max plus or minimum plus algebra. Secondly, this is a into b. This goes as a tropical multiplication b, and that goes as a plus b. And this is a plus b regardless of which algebra you're working in, whether it's in tropical, whether it's in min plus or max plus. And 0 was our additive identity. So it was an identity for plus. So the identity for this, which is basically the identity for max or min. So for max, we wanted the number to always be lesser than a, right? So the max identity is equal to minus infinity. And the plus infinity is equal to, and the minimum identity is equal to plus infinity. Alright, so these are your identity elements. These are your identity elements for tropical addition, depending on which algebra you're working in. Okay. Similarly, you had multiplicative identity. It used to be 1. Now, you want plus id is equal to a, right? And now a is just plus, so a plus id is equal to 0. So your tropical, so 1 basically gets converted to 0. Okay, big circle over here for emphasis. And now lastly, the expression of 1 by x gets converted to basically minus x. Why is that? Because when we convert, let's say this is normal over here, and let's say this is tropical down here. So exponentiation becomes multiplication. So x to the power minus 1 is equal to minus x. Okay, now I'll continue with Maslov dequantization.